I'm very happy to be here and then to present the results of the BAO first year analysis. So I will start with this talk, and then Licia will follow at the end of the talk. And before we start, then we thank all of our sponsors and all participating institutions. So as you may have seen today, there are a bunch of papers in the archive. So there are in total, I think there were like around 12 papers. 3 of them are what we call key papers, that they are essentially presenting in an alphabetical order the results, the main results of the DESI BAO. Essentially, it's BAO in the galaxies and quasars, then BAO in the Lyman alpha, and then a third paper explaining the cosmological interpretation of this BAO. And there are a bunch of supporting papers which essentially dive into all the details about systematics, how we've done the measurements, etc., etc. So all the details that 90% of the people don't care about these details, but they are important. And if you are doing your thesis in a related topic, then you may want to read about these other papers as well. So this is, just to put you in context, this is like the evolution of a spectroscopic redshift survey. So for the non-experts, there are like two type of redshift, two type of galaxy surveys. Those who take essentially photos in different bands, which we call photometric. They are very good for doing weak lensing. You have sizes of galaxies, but the precision in terms of redshift, so in radial distance to the object, is poor. On the other side, we have a spectroscopic surveys, which is what is shown in this plot, and that is one of them, which we don't take photos, so we don't have an actual photo of the galaxy. But what we do have is a very, very detailed spectra of that galaxy. And then this helps us to put constraints on the distance to the galaxy. And this is what DESI has been doing. In the past, we start at the end of the 80s with the CFA surveys with only not even 2,000 objects. And then as you see, as the time progresses, the technology has been increasing. Has been improving, and then the number of galaxies have also been increasing, and you see like a linear relation between the log number of galaxies and the time. And now we have DESI that by the end of the 5th year, which is in around 2 years' time, we will have around between 30 and 40 million galaxies. Right. So the best night of DESI got around 200,000 objects, which is like the full 2DF survey in 2003. Also, with just 1 year of DESI data, we have surpassed the full previous survey, which was the BOS and EBOS, which is here labeled as SDSS, which it took like 20 years. And then in 1 year of DESI, it just essentially overpassed this number. And we will see now how we managed to do so. So just for a comparison, maybe you cannot see it very well in this image, but this is an image of the position of the galaxies at the beginning of this CFA2 survey, and now in DESI. So you see, like by comparison, how complete this is. And so we have some web page in the DESI server where we just essentially write down all these observing records. As Licia was saying, the number of objects in the night. So we have here the night, the observer, and the supporting observer, and among these redshift, we are proud to say that ICCUB was observing in one of these nights, which was the record of getting the best positioning accuracy in microns, which is essentially how good the fiber, which is essentially the robot that is moving the fiber to get the redshift, is just positioned to the object to get. So this is just around like 2.6 microns. So this is, I think it's the size of the human hair. So just to get an estimate of. So this is essentially an image of the 1 year data of survey, and just for comparison, you can actually go into this webpage and slides, but I will no, here it is. So this is, sorry, this is for the previous survey, SDSS was an EBOS, which took 20 years. And this is DESI just with 1 year. So just can swap it by comparison. So just, if you don't know what is this wedge here, that you don't observe, this should be a sphere, but then our own galaxy essentially blocks light into the direction of the plane. So this is essentially the areas in the sky we can observe because of our own galaxy, but otherwise should be a sphere. And this, we have like a northern part, which essentially observe upwards from the plane of the galaxy, and the other, which is observed downwards. And this is for the DESI 1 year. So there are a lot of things you can do with this spectacular data set. So you can do essentially clustering. You can actually wonder what are the constituents of matter, which is the physics of inflation. You can also exploit what we call the standard ruler, which I would explain briefly afterwards, which essentially is a geometry test of our distribution of galaxies. You can also do other stuff like redshift space distortion that essentially look at how structures grows at small scales. And you can also do homogeneity and non-Gaussianity tests at large scales, and many other tests. So there are a bunch of physical tests you can do with DESI data, but in this release and the release that has been shown today, the only thing we are going to exploit is the standard ruler. So this is like the DESI telescope. It's located in the so the DESI instrument is located in the Mayal telescope. Is a 4-meter telescope, and the key things is that we have like a 5,000 robotic positioners, which essentially are moving the fibers that we just essentially moving the fibers essentially to position them to the exact positions in the plane of the sky where the galaxies we are interested are. And this is like the new thing of DESI, that these fibers can move automatically for each patch of the sky we are observing. So these robotic positioners move the fibers, which get the lights and bring the light to the 10 spectrograph with 3 channels, that they are essentially the responsibles to get the accurate spectra from them. This is an image, sorry, this is an image of the positioners, the robotic positioners. There are 5,000, and attached to them there are the fibers. And yeah, so, and this is an image of the spectrographs, and there is a person here just to for scale purposes. And there are 3 spectrographs in the different channels. In total, there are 10 of them, which are in this photo. So it's a massive amount of technology service put at the service of astronomy, or cosmology in this case. So just to get an idea of how many galaxies per patch of the sky that DESI can get. So this is an image of the sky. I think this is the Triangulum galaxy. And these are all the targets that we are observing. And you have here, they have been identified from a previous photometric survey. So we know where the galaxies are. And now when we go with a telescope and to the region of the skies where we know exactly where the galaxies are, with this information, we move the robotic fibers into the exact position of the galaxy. And then we essentially collect this. Sorry, this is the computer is. So in total, the plane of the sky we are covering is massive. It's 3.2 degrees. And as I said before, this is the Triangulum galaxy. But essentially, the full image you can get essentially like an image of Andromeda. And there have been some tests we've done capturing light from Andromeda. And it fits entirely well, well within this part of the sky. So these are like the different type of objects we observe. We observe quasars, we observe ELGs, which are emission line galaxies, LRGs, which are luminous red galaxies, BGS, which is a bright galaxy sample nearby to us. And then we also have another program, which is the Milky Way Science, that it's not related to cosmology, and essentially we observe Milky Way objects when the conditions for observing like deep objects in the sky, they are not good enough because we have poor seeing or we have moon, and then we essentially move our telescope to secondary targets. Here we have a number density of the different targets. So as I said, as a function of redshift, so nearby targets are BGS. We have a huge number density of objects, and then LRGs, then ELGs, and then quasars, which are more sparse. And this is a footprint of the sky of what DESI year 1 has been observing. So we have the northern and the southern patch of the sky, and the different colors essentially show the different passes we are making, because every time we pass for a region, sometimes we don't get the 100% of the target, so we need to do several passes, and this is what is shown here. But by the end of year 5, we will get essentially all this region well covered in the color of red. So in total, in the 5-year program of DESI, we are foreseeing to observe between 30 and 40 million redshifts. We essentially will target around 13 million BGS galaxies up to redshift 0.4, and then 8 million of LRGs up to redshift, or between redshift 0.4 and to redshift 1. And then ELGs, we will obtain around 16 million. And then we got quasars at higher redshift. Then I'll see where 3 million quasars. And then also at even larger redshift from the quasars, we also get information on the distribution of neutral hydrogen through a technique that is called Lyman alpha, which essentially is based on observing this neutral hydrogen gas illuminated by background quasars, and then looking at how this light from the quasars, they have different absorption lines because of the presence of this neutral hydrogen. Then we can also infer the presence of matter at scales, at distances where we don't observe galaxies, or there are like very few quasars. So this is essentially what is explained here, the Lyman alpha forest technique. So you see here the spectra, and then you see here the absorption lines of the neutral hydrogen gas, and then essentially by measuring these absorption lines, then you can say where in the sky at which distance there is hydrogen gas, and you can also do a video technique with this. So this is what was said before, and then what we are going to be exploiting essentially here is the baryonic acoustic oscillations. So some of you may already know what the BAO are, but then for those who doesn't, then I'm going to explain briefly what these baryonic acoustic oscillations are. So we have C and B times before decoupling, and before decoupling we have this plasma, which are essentially between photons and baryons. They are coupled. Electrons are free. They are not contained in atoms yet because the temperature is very high. And this means that we have an interaction between photons and electrons. And electrons are also coupled to what we call to protons. For these purposes, I will refer to electrons and protons as baryons, although I know that an electron is not a baryon, but in cosmology we call it this way. To distinguish between photons, which are radiation, and dark matter, which are not baryons. So we have this plasma gas, and then we have essentially two effects. One is gravity. So there are like potential swells of dark matter, which attracts the baryons, and then baryons are coupled to photons. So when you put all together, then you are compressing baryons with photons, and essentially there is a point where they don't want to be compressed, and they start expanding. And then they leave the potential well until this pressure is less, and then they will follow again. And then there is this oscillation between gravity and pressure radiation from photons, which creates sound waves in the plasma. So the plasma is a fluid, and these are vibrations, and vibrations produce sound waves into the fluid. So this sound wave essentially will expand at a certain speed, which is around 1/3 of the speed of light, and will expand through the plasma. And this expansion essentially continues until one moment, which is the coupling, where the plasma disappears. So there is a moment where the temperature of the plasma is low enough that the electrons start being captured by the protons and forming hydrogen. And then once the hydrogen is formed, then the hydrogen doesn't interact with photons, and then the plasma essentially disappears. And if the fluid disappears, then the sound wave cannot travel anymore and remains at a certain distance, which is essentially determined by the speed and the time. So the speed we know because it's related to the plasma equation of a state, and the speed and the time is essentially the time it takes until the plasma disappears. That's the coupling. So this is plasma physics. We understand it quite well. So this sets a typical scale that we can determine very well in the CMB, right? So this scale is imprinted in the photons. So when you observe CMB from photons, when you observe the photons of the CMB and then you compute the spectra, you can see these oscillations, but it's also imprinted in the baryons. You cannot see the baryons at CMB time, but you can see the baryons at later time, which are essentially the stars and the galaxies. So when you look at the stars and the galaxies at much, much later times, at recombination, obviously when the stars start forming, this is below redshift roughly 5. The coupling takes time at around redshift 1000. So even way after is the coupling, there is this imprinted signal in the distribution of galaxies, which is the BU. And then we can detect that by looking at how two galaxies are separated. So we have this length, this typical length of the BO, the distance that a sound wave has traveled in the plasma, imprinted not only in the CMB, but also in the galaxies. And this is very important because this is essentially what we call a standard ruler. There is something in the sky, we know which is their physical length. And if we know which is their length, then essentially by measuring their angle in the sky, we can actually infer their distance. And this is very important in cosmology because we always have problems inferring distance to objects. And this is a technique that we essentially exploit here in order to study how the universe has been expanded. Right, and this is what I essentially explained. So how or what do we measure from the BO? So the BO in principle, this overdensity is essentially a sphere, and you can essentially exploit it in two ways. You can exploit on the size of the sphere. So depending on which cosmology you think your universe is, then you essentially will be modifying the sphere when you transform redshift into distances. But if you know the exact size of the sphere, then essentially you can adjust this cosmology transforming redshift into distances to say, hey, this is the 150 megaparsecs I know the BO is, so this is my constraint on the cosmological model. And this is what is the isotropic BO. But there is another thing. So you can not only measure the BO in the angular distance, but you also can measure the BO radially. And it happens that when you transform redshift into distances, the BO physical size changes differently across and along the line of sight. So if you got your cosmology wrong, then you're essentially going to distort the BO, and you are not going to observe a BO which is a sphere, but an ellipse. But you know that the universe is isotropic, so the BO has to be an isotropic structure. And therefore, by imposing this isotropy across and along the line of sight, you can also infer something about your cosmology. You have here is going, so the anisotropic effect. So you distort the BO along the line of sight differently than across the line of sight. And you can express this like in two bases. So you can distort this spherical BO in the basis of anisotropic shift plus an anisotropic shift. So this is those two things here. But you can also express this as a distortion in the transverse and in the longitudinal direction. So this is what we usually call for the visionados, the distortions in terms of alpha isotropic and Alko-Paczynski parameter. So this is alpha isotropic parameter. This is the Alko-Paczynski parameter F, or in terms of alpha parallel and alpha perpendicular, which would be these two distortions here. So how do we see the BEO in the distribution of galaxies? So what we need to do is to compute correlation functions, because essentially we don't see BEO by eye. This is a very subtle structure which cannot see by eye, and you can only be seen when you do a statistical treatment of the typical separation of the distances of two galaxies. So in terms of the correlation function, this is much simpler to visualize. So the correlation function is a mathematical object that tells you what is the probability of finding two galaxies separated by a certain distance, which is expressed. So this is the isotropic, and this is an isotropic, but just for the simplicity, focus on the isotropic right now. So because of clustering, when you look at the scales very close, you have like very likely to find another galaxy. So if there is another galaxy here, you have very likely to have another galaxy close by because they interact gravitationally. So you have like something up. And then as you move away, then you have less probability. So you go down. But then there is a scale, which is the BEO scale. And then you get a slightly more probability to keep going down to the probability. So this is because you have this overdensity imprinted. So the sound wave in the plasma carry like an overdensity, exactly 150 megaparsecs, or 100 megaparsecs over H, overdensity that was traveling. So when you keep going away from a galaxy and then you reach this standard ruler scale, then you have a slightly more probability of finding another galaxy. And this is what you see here. And essentially, this is how we identify the BEO scale. So we just do a correlation function, do pair counts, and do an histogram of the pair counts, and then we see that there is this typical distance that we see here. And we can do this in the isotropic, which essentially is like this isotropic changes of the BEO, or we can also do it in the anisotropic part, which would be the Alko-Paczynski, which is contained in these other red points here, which are the quadrupole. And you can work this here in the configuration space in terms of the distances of galaxies, but you can also work in terms of the power spectrum, which is essentially the Fourier transform. You can think of a Fourier transform of the distances. So you can work in the space of frequencies. So essentially, it's the same information, is the same idea, but it's slightly different tools and different ways to get more or less the same information. So this is just for those who are into this. So we have essentially two distances we can work out in cosmology, the angular distance and the Hubble distance, and how this is related to the angle we measure in the sky or the dip in redshift, and how this is compared to the BEO scale, which is called here RD, and how this is related to the cosmological parameters, the usual omegas, which are essentially our target. So obviously we need, if we want to calibrate distances, we need to know which is the size that the sound wave has traveled. So we need to get this information from somewhere. Typically, what BEO does is to calibrate this from CMB. So ask CMB, which is this distance, and then with this distance, you calibrate the galaxies, which is called the inverse distance ladder. So it's inverse because you go to the very past and then look at it and then start building your ladder from something in the past, which is the size. But you can do also another approach when you calibrate distances, which is looking at objects nearby that which, in this case, not size, but which luminosity they have, which are the standard candles, in order to build up your distances. So this is a usual distance ladder. So parallax, you identify Cepheids. Cepheids, they are a standard candle because you can relate period to luminosity. You calibrate distance to the Cepheids, and with the Cepheids, you look for another object, their luminosity. These are the supernovae type 1a. they explode at a very fixed mass and then have a brightness that is standardizable. And you can also use Cepheid to calibrate supernova, and then you can build up the ladder to that. And you also could use supernova to calibrate the BEO. So you can either use the CMB or the supernova, and then you will get this calibration of the BEO. So something on the top of this is when we are doing our analysis on the data, we don't want to be inferred by previous measurements, right? So this is a problem we have in physics, that when we do a new measurement, then we essentially know which are the actual model or the standard model of cosmology. So we are sort of affected by this human bias. So in order to avoid that, what we've been doing for the first time in a cosmology spectroscopic analysis is to do a blind analysis. I'm not going into the details of how we are going to blind, but what I can say is that what we are doing is that we are distorting our map of galaxies, which are essentially two angles, right ascension and declination and redshift, and we are going to essentially apply a pre-processing into this map to essentially produce distances that they are wrong, or they are blinded. And we are always going to work with these wrong distances, that they are going to give us a wrong cosmology, but we know that it's wrong. So essentially, we are not going to care about the specific values of the cosmology we get when we do this first analysis, and when we start observing the galaxies and check that everything is right. So it's only at the end of the analysis that we are going to remove this blind layer, and we are going to see which is the actual cosmology that our universe returns. And it is something that we've been developing here in the ICCUB and has been applied to the final analysis of this. So there were like a series of tests that they were passed before unblinding. So that was happened at the end of December in the meeting in Hawaii. And essentially, this is the moment. I mean, I was unfortunately attending by Zoom, but there was the moment during the meeting of Hawaii. I don't know, it was like 10 p.m. only. They were trying to make it Europe friendly when we removed the blinding, and then we essentially saw which are like the results that DESI were returning to us in terms of this alpha isotropic for the different traces, for the different distances, and this is for the Alcoplechinsky parameter. So yeah, so we have like different redshift bins, different distances provided by these different tracers. We have one BGS, two LRGs, one LRG plus ELGs, a quasar, and a Lyman alpha. In total, it should have been 7. Not, I just missed some of them. This is the power spectrum. This is the correlation function. You can see the peak in the isotropic part by eye. Is a very, very strong detection of the BEO. That's something that might seem natural, but in the past, the detection of the BEO was hard. And this is essentially the same information, but extracted and more focused when you remove the broadband and you just plot the peak with respect to the broadband signal. So you see how beautiful it is that this very, very well identified, especially in the LRGs where we have much more signal. So there is no doubt that the BEO exists, no doubt that this well identified. And actually, for this first time, the position where we identify the BEO aggregate position is around 0.5%. So we are what we call deep into the regime of precision cosmology, below 1%, finally. This is the significance of the BEO peak. And then you see in terms of sigma detection, so delta chi-square with respect to fitting a model with no BEO. So this is essentially telling us how well detected it is. So in some cases, it's maybe around 4 sigma in the quasars where the BEO is not that strong because of is a sparse sample, so we don't have any objects. But when you go to, for instance, this guy here, we have like a 9 sigma detection of the BEO. So it's super, super strong. And before, with just 20, the full SDSS in 20 years, we got an aggregate precision of 0.6. So now DESI 1 year, it's essentially the same, even a bit better. So by the time we finish this, there's going to be essentially factor of 2 improvement. So this is how the diagram was before DESI. So essentially this slide here shows the angular BEO, and this shows the isotropic BEO. And these were like the measurements essentially from BOS and EBOS. We had actually 3 energies, 1 quasar, and there is another Lyman alpha, which is not plotted here at 2.5. And then there were other experiments like Wiggle Z and 6DF, but the precision of those were much worse. Here, the straight line is the standard Lyman, the standard lambda CDM with Planck for reference. So you see here that more or less the BEO was in agreement with the predictions of Planck. You see some discrepancies, which is like few sigma, so nothing to worry about. And this is essentially the same, but in these other variables, right? So you have this isotropic and anisotropic BEO, but you can also express this in terms of this transverse and longitudinal line of sight. It's just 2 ways of essentially expressing the same thing. And in color, this is like the new DESI results. So you see here how the error bars are way smaller. I'm just going to leave you a few seconds to compare and trying to see how well or not well they agree with the all lambda CDM. So just as a spoiler, there is a guy here which is a bit off, and also a guy here which is a bit off. This is going to be interesting. Yeah. And this guy a bit as well. And this guy a bit as well. So there are like some deviations, especially with respect to the previous measurements, that we will need to think about and see whether they are consistent. Think that we are observing not exactly the same data. So when you observe different areas of the sky, you expect to have some shifts and fluctuations, but then this is always difficult to disentangle if you don't have enough data from actual signatures of new physics, potentially. So we have done very robust test of systematics. So we have tested like several things, and there is a comparison of what is the maximum shift that we expect if we essentially ignore correcting for some of the systematics. The most important ones were the imaging systematics, that they are related to how we correct different areas of the sky by the fact that we haven't observed essentially the same number of galaxies. So we know that there are areas of the sky that they have essentially different observing conditions, and therefore we miss some objects in some areas with respect to other. So that creates like a non-uniform distribution of density of objects across the sky, and these imaging systematics aim to correct for that. But this correction might not be perfect and might be introducing something. So we wanted to quantify how much non-correcting was affecting the BEO, and essentially you see here, it's very robust. But even with this, we have propagated these small error bars into the final results. Right, so this is just a summary of this different systematic test, and ICCUB also was involved with a former postdoc here, David Bianchi, who was working in the fiber assignment. But yeah, I mean, there are essentially details. And yeah, this is also like a nice plot of visualizing like the same thing. So we have essentially the BEO across the line of sight, the BEO along the line of sight, the isotropic BEO, and the Alko-Paczynski. So the comparison between the along line of sight and across line of sight BEO for the different traces, and the dashed line is the prediction of Planck based on lambda CDM model. So it's not a fit, it's a prediction. So you see that there are some differences, but well, they are. So what does it mean for cosmology? I'm going to let Licia present this part, which probably is the one that you are more interested in.
Okay.
Yeah.
Yes, let's go. So the first question you ask when you get this type of new data is the lambda CDM model still okay? So what you show in this plot are in the two projection of the isotropic BAO and the ratio between the line of sight and the plane of the sky and the FAP. With two model data, with the error bars, with two models, the Planck, best fit lambda CDM plus or minus 1 sigma, and the best fit now without error bars of that come from the new data. And so you see that, yes, it's new data, and there is a little bit of a difference, especially down here, and it's driven, surprise, surprise, by the two data points that are around redshift 0.6, which are the one that had the little circle in the previous slide and the one that differ from Sloan. And what we're seeing here, we're going to see is going to have influence on everything else you say beyond that. It's at the 2 sigma level in a couple of data points, the 2 sigma level into data points, the moment you fit, depending on the number of parameters and where the model you look are more or less freedom, you will be able to fit or not fit whatever is going on in here. So, whoops, what happened here? So after we check whether it's okay in the distances, which is the distances are measured and are model independent, it's just the distances. And then you put a model through it and see whether they agree or not. Now we move rather than on compressed data, those distances are basically compressed data, no model involved, except homogeneity and isotropy, to something else, which is something close to the theory, which is cosmological parameters. So it should be clear to those that are doing some cosmology that if you measure angle and distances, you can't measure, sorry, angle and redshift, you can't measure absolute distances. So you can't measure an Hubble constant out of the BAO unless you calibrate that distance ladder. So without calibrating it in any way, even if you do assume a model of the late universe, what you will be able to measure is this combination, which is the size of the sound horizon of the radiation drag, the size of the standard ruler, of course in units of little h, because you haven't calibrated this yet, and a parameter about the expansion history of the universe, that is it the same as the lambda CDM, or is it more curved or less curved, which is encapsulated in omega matter. And so if you had the BAO at only one redshift, you could not disentangle these two numbers. You have one thing, you want to number, you can't, you would have a degeneracy. But since you have many samples that span redshift, if the sample is at a very thin redshift, right? You have degeneracy. As you change the redshift, the degeneracy changes in this plane. And as you add the data set that cover broad redshift range, this is like shrinking, you combine it all and you get a little thing down there. So this is in a lambda CDM model. But then, and then you can zoom in and you can look at the comparison with the SDSS, combine SDSS plus DESI, and for comparison, the cosmic Mercury environment and the lambda CDM lands there. So in this projection and in this model, there is quite a good agreement between the two. Now, the CMB, yes, assume an early physics model for the early universe. The BAO does not assume yet an early time physics, as long as one does this. So what about other data, and what about curvature? At this moment, you bring in other data. As you bring in other data, for example, data from Big Bang nucleosynthesis, you can say, but now I can't constrain the size of the standard ruler because I assume standard early time physics. If I assume standard early time physics, I know the equation for my little RD. And that equation for the literal RD, with assuming standard early universe physics, is just an integral. It's an integral that depends on omega matter, depends on the radiation, and depends on the physical density of baryon. The radiation we know because we know the temperature of the CMB. The density of baryon, Mills provided the most updated and conservative constraints. It's called BDN. And then you are able to break that degeneracy, and you can start putting constraints in the plane H naught versus omega. You can add more data. You can add the position of the first peak that comes from the CMB. That is, gives you some information about the distance between you and the last scattering. And then you can instead add the full information about the cosmic method. And so you narrow down the error bar around omega matter, and you start getting number for the Hubble parameter, which you can see is in the realm of the early time cosmology. So in the early time Hubble doesn't agree with the Cepheids, it seems to agree with the CMB, for surprise. At least it calibrated on the early time physics. And then if you add the curvature, there is no evidence for any deviation from curvature. If you remember a few years ago, there were claims that if you take the CMB alone, Planck has some preference for a universe that is not flat. The moment you add large scale structure data, then that preference goes away and the constraint collapse again against flatness. So yeah, that's still consistent with that. And if there's some numbers that you want to remember, here they are with the type of error bar that you can get on this parameter. Okay, so let's move on. What about dark energy? So far in lambda CDM, the cosmological constant, the lambda is a cosmological constant, but who says it has to be constant? The problem with 120 orders of magnitude mismatch in the energy, in the vacuum energy. And so traditionally one can say, well, let me say that the relation, the equation of state parameter, that is the relation between density and pressure, is not described by a -1 like it is for the cosmological constant. It's something else, and say that it's something different than that. Let's take a number, let's consider it constant. We know it doesn't have much physical motivation, but it's better than nothing. And so for this parameterization, then you start playing this fusion game where you have a sort of high-dimensional space where you have omega matter, omega lambda. In this case, the universe is considered to be flat. Actually, you have W, you have H, you have all that, and then you put it all in an MCMC and then project down and combine different data. So the supernovae constrained in this plane, this direction. The cosmic microwave background constrained this direction, and the BAO is a potato this direction here. And so the BAO, yes, by themselves constrain break the degeneracy between W and omega matter. But then when you combine them with cosmic microwave background and supernova, then you get a tiny little constraint that is centered around the -1. That is, from this type of analysis, there is no hint or indication of any deviation from a cosmological constant. That is, the relation with pressure and density is described by a -1. And then, very happy with this, you keep on going. It's important that from DESI alone, you already get some constraints, which are not to be ashamed of. And then you say, okay, but we know that the W constant is not physically motivated. It turns out that there is a parameterization of this dark energy equation of state parameters, which can be mapped into many models of dynamical data. So the moment you go away from a cosmological constant, it's reasonable to expect that you have some dynamics. If you do have some dynamics, it's not reasonable to expect that W is a constant. So if you have some dynamics, it always turns out that at least in a range of redshift, you can map your model in this sort of parameterization where this is a constant and this scales with redshift. However, the specific, so this kind of model tends to constrain this number always at some specific value, which is where you have most of your statistical power of the data. Because this kind of parameterization is like, you know, a linear parameterization in redshift, but you don't observe the entire range of redshifts, you observe a small range. And that's where all this game are gonna. So the other thing before interpreting this plot, that of course it's marginalized over all the other cosmological parameters and then projected in this plane. And there is a inbuilt prior in the analysis, which is that you want that at all redshift, this number plus this number is always less than -1. And of course, the stronger constraint is a redshift 0. And so this region up here is not even excluded, it's just cut out by the prior. So some constraint hit the prior, but that's to be expected. And you want to do that because you need some deceleration time. So you need deceleration and acceleration. And if you don't put that constraint, then it's that nonsense.
But we need that really. Don't the data themselves should tell you that?
So yeah, so the data themselves will tell you where you have enough data. So for example, BAO plus supernovae will. BAO plus CMB will. But if you just take BAO alone, then you can't, because you see this more range in redshift, and you don't know what's going on at redshift much bigger than 1. That's where. Yeah.
So it's really only the prior is only significant of the BAO.
Only, yes.
Only, right?
Yeah.
Well, Pantheon.
And Pantheon.
PO plus Pantheon.
Yeah.
Well, the is very little, but
Yeah. But it's still relevant.
And there is another prior at -3.
And there is another prior here. So the fact that it's not plotted, it's because it's a prior. So when you do this, if you take, as I say, DESI alone, DESI plus CMB, or DESI alone and DESI plus CMB, and in this case a little bit, there is this degeneracy, which is the prior. You start breaking this degeneracy and not being too dominated by the prior only when you combine 3 data sets: the CMB, the DESI BAO, and a supernovae data. Now we need to spend a few words to discuss what are the supernovae data. So the Pantheon plus supernovae data has been out for 2 years, and before there was the Pantheon supernovae data that was out for another 2 years. The Pantheon plus has been reanalyzed, reduced systematic, propagate them, etc., etc. But then in the last few months, and actually this paper was in archive recently, 2 new supernovae came out. In reality, the Union 3 has a lot of supernova in common with Pantheon plus, but it's a completely new way to analyze the data. It's a way that doesn't give you any intermediate product. You throw in a supernovae and you get out the cosmology, and it's sort of different to do, so difficult to compare directly with the intermediate step. The DES-CR5 is a completely different way of doing supernovae, comes from the DES survey. And then it's also independent, so it's independent. So this was out like really a few days ago, became available. And so if you do that and you combine CMB plus DESI BAO plus supernovae, there is some indication that there is a deviation from the lambda CDM fiducial value, which is W naught -1 and WA equal to 0, which is 2.5 sigma for Pantheon plus, 3.5 for Union 3, and 3.9 from DES year 5. Please bear in mind, we have combined 3 different data sets. The data sets that DESI has control over are this one we have no control over. This has been used by the community since 2018, has been deconstructed and reconstructed. So this is a little bit more under control by the community, not necessarily by the collaboration. So what's going on? So on the left-hand side is seen from very far away, the Hubble law renormalized by 1 plus Z, where you see the Planck lambda CDM and the best fits that one gets for the different models with the error bar. So this best fit that you saw in the previous plot with the same color scheme. So you see there's from back in the room, you probably don't see much difference. In terms of expansion history of the universe, the difference is not that big. But then if you zoom in and you actually plot also the error baryonic, and you plot the and you zoom in into what's going on, and then you start seeing a little bit some differences. And then you can start ask yourself, what is driving that signal? Where is that signal coming from? And it wasn't me, it wasn't the Lyman alpha. It wasn't the pointer redshift around 1, but it's the samples that are at redshift around 0.6. And we've seen this point before, but then for this point says it wasn't me, but it says you're aware too, because here I plot the line of sight information. And this is not the whole information that we have. It's the easier information for you to interpret because it's a coupled as a function of redshift normalized by the scale, the sound horizon. But there is also the information on the plane of the sky, and in the information across the plane of the sky, this one was the weird one and not this one, while this one is the weird along the lines. So we go back to what was happening in the difference between Sloan and DESI with that data point around redshift 0.6. That's what is driving all this. So now this brings us back to the famous or infamous Hubble tension. Everything you wanted to know about the Hubble tension whenever there to ask, it's in this review, which is going to be published very soon. But let's see what grain of sand can DESI add to this discussion. So what is the DESI view on H naught? Well, as we were saying before, from BAO alone, you can constrain only what is the BAO view of the normalization of the standard ruler and a parameter that describes shape of this function history. It is E of Z, which is the H of Z, but without the H naught in front. And so in the previous plot, I show you what happened for the lambda CDM model. As you start relaxing the assumption about the shape of this function history, like you had the curvature, you had a constant equation of state parameter, you have the famous WWA, you have the WWA and curvature, then the constraint in this plane relax. Then you want to add more data to break this degeneracy to get to H. And depending on the data you add, then you break the degeneracy and you get some numbers. So let's see in the big picture. CMB only with no lensing and CMB with lensing land there. We have been knowing that since 2018. Planck lines somewhere above 67 with some error bar which is below 21, smaller than that. DESI needs to add something. So DESI plus BDN, thanks to Niels, lands here. So it's still in agreement with the cosmic vector. Then you can add the position of the first peak. It doesn't budge, the error bar shrinks a little bit. Then one can add RD that comes from the CMB, and then one runs there. And then you say, but this was weird compared to Sloan. Why don't we add in the Sloan number, given the fact that the Sloan, especially in that redshift where things are going weird, has a bigger volume. And then you keep track of the covariance. And then you can do DESI plus Sloan, and this number is a little bit lower. And this is the old Sloan BAO plus BDM just updated to the new BDM, and then it's here in agreement with the previous Sloan analysis. And then for comparison, the measurement based on the direct distance ladder, these come from the Wendy Freeman group, and this comes from Adam Rick's group. And this is the usual discussion about that. So if you want to count the number of sigma, then you can read them depending on the data on the underlying model, and depending on the data combination, you can get between 4.5 sigma in a lambda CDM to, of course, if you leave a flexible expansion history, then the number of sigma. So, but DESI plus BBN constraint break this degeneracy, and you get a 1.2% measurement on the Hubble constant, which already is in more than 3 sigma tension, which is without even considering the CMB. So the BAO are land on the early camp. You can't say that Planck got their analysis wrong, because we taken CMB completely out of the equation and still the number is the same. Okay, so thanks to Niels for giving us the BBN number. So finally, neutrinos. Now, remember, we only do BAO, so we can't see the signature of neutrino. The signature of neutrino in large scale structure is typically the suppression of the growth of fluctuation below the free streaming length. But what we're doing here, we're just doing expansion history. We can't see that. So whatever we are seeing, it comes because one is breaking degeneracy. So let me see what happened if you change the neutrino mass from a lambda CDM model, which has a fiducial neutrino fixed at 0.06 and move along the CMB degeneracy and see what happened to the larger scale structure power spectrum for different neutrino masses. You see that this suppression, because of this cancellation and cosmological degeneracy, almost cancel out. There is some effect on the BAO. Most of the effect is on the amplitude. So since we are not looking at the amplitude of the BAO, we're just looking at the distances offered by the BAO. We are not seeing neutrinos. What we are seeing is breaking the degeneracies that are present in the CMB. And so this is the result. Sum of neutrino masses, some unnormalized posterior. Now, we know that the sum of neutrino masses needs to be above 0.06 eV because there are oscillations. We know the masses, the square mass is splitting, so we know can't be 0. But if you want to say that cosmology puts some constraint on neutrino masses, you may want to give it to be like a parameter that even be 0, and then see what happens, because the larger scale structure, as again, only breaks parameter degeneracy, is not modeling the physics necessarily of the microscopic physics of the neutrino. So see this as an effective parameter and see how it can be interpreted. And so these are the posterior distribution with the CMB only and the addition of DESI. So it's a big tightening of the error from the CMB only. So can we see how this degeneracy are broken? Oh yes, of course. If we plot H0 versus the sum of neutrino masses, the CMB show this degeneracy. Now the BAO comes in and constrain, once you put a model in the early universe for the standard ruler, basically cut this degeneracy in this direction, and that's why you get this 5%. Then you can go and look at the delta chi-square, because those of you that know about neutrinos know that here we are looking at something that is unphysical. And so if cosmology prefer a value of an effective parameter that is unphysical, then definitely you haven't seen neutrinos, or definitely you are telling me something else, but we are telling nothing about neutrinos. But it turns out that the delta chi-square between that and this is not that significant, so let's not jump out of the window just yet. So this is done by assuming the degenerate hierarchy, because it doesn't really matter. It doesn't really matter at this level, but it was checked that.
Did you impose normal inverted? I mean, you didn't impose the mass split.
No. So we are imposing degenerate because it was tried both normal and inverted. Again, going all the way to 0 though. And it doesn't really matter at this point. The moment you detect something, then yes, you will have to go and actually do the things properly. But at this level, it doesn't. So that's the bound 95%, DESI BAO plus CMB, but it is prior dependent and model dependent. So if I now here impose a prior, it has to be physical, it has to be above 0.6 eV. Of course, this is will not be the 95% bound. And it depends also on the model. The moment I say it's not a lambda CDM background, but it's a W or WWA background, of course, this constraint relaxes because the breakthrough generality, we are not seeing the neutrino smoking gun. So in summary, a DESI plus VBM gives 1% level constraint on H0 and is still in tension with shoes. There are very tight constraint on curvature. The universe is still flat after all these years. W, when we consider it constant, is still about -1. When you do a WWA parameterization, then a lot of things happen, and we've discussed that already. If you want to know more, look at the appendix of the cosmology paper. And there are tight limits on a parameter that can parameterize the sum of neutrino masses, like an extra parameter beyond the lambda CDM model. So it's the most precise BAO measurement overall so far, where you just integrate the measurement of the distances. But what matters is not just the precision of the measurement itself, also which redshift you measure. Because if you are after dark energy properties, measuring distances very precisely a redshift above 1 is not of much use, because there's no cosmological constant at redshift above 1, and there's no dark energy at redshift above 1. So there is, but it's not relevant for the evolution of the universe. So it's the first BAO blind analysis done at the catalog level. So we are very proud of this because we developed the blinded here. You can do the blinded in a very simple way. Whenever you do your summary statistic, you just don't look at the axis of the plot, and then you do the analysis this way. But here we've done it directly at the catalog level, which means that a lot of systematic check could be done on the data while not knowing the cosmology. And so disentangle the checks on the systematic from the checks on the cosmology, and not end up in this circular argument that you check the systematic until you get what you want from cosmology, and then once you get what you want from cosmology, you quantify your systematics, and then you publish. So this vicious circle could not be done. So it's the highest precision galaxy BAO at redshift about 0.8, and then it is the first significant BAO detection and cosmological interpretation from the emission line galaxies. And I'm saying this because this is important. These are the future for high redshift large volume surveys. So if you want cosmology and precision, you need a lot of volume because you're limited by cosmic variance. And if you need a lot of volume, you need to go to high redshift because, you know, you have a bigger area that you see given the angle. But then if you go to redshift above about 0.7, you run out of LRGs. And so the only object that remains are ELG. And if you, and it was a big question mark at the beginning of actually promoting DESI as the next stage 4 BAO survey. It was like, you want to go with ELG, but nobody has ever done BAO with ELG. How do you guarantee that this object will behave as nicely and as the LRG behave? And this is the first indication that so far they are behaving. And so I'll stop here with a summary of how the DESI BAO analysis is different from all the previous ones. Thank you.